Moving on to our next presentation, we have Iddo Eldor, and the topic is supply chain reaction.
So, hi everybody. First time in Budapest for me. My name is Iddo. For the past decade or so, I've been working for several cyber offensive companies as a vulnerability researcher. On Sunday, I'm heading to Paris, to Hexacon, to pass a 4-day course I wrote about real-world VR on instant messaging apps. I now work at Mirror, securing software supply chain attacks. Software supply chain is a wide range surface for VR, and I will try to cover it in the following 20 minutes or so. So, the software supply chain is anything and everything that touches an application, its development, through the entire software development lifecycle, the SDLC. This includes third parties and proprietary code, deployment methods and infrastructure, interfaces and protocols, and developer tools. So, supply chain attacks has not only increased in volume, but also become more sophisticated, involving APT actors. 45% of the organization will experience a software supply chain attack by 2025. This prediction was made by Gartner. So why should companies worry about it? So basically, ensuring continuous availability and reliability of their digital products and services. This translate into sustained business operation, minimizing downtime, preventing data loss, preserving customer and safeguarding the revenue streams. Supply chain attacks are often targeted sensitive data, such as intellectual property and customer information. For SaaS, software companies, the biggest challenge with supply chain attacks is that as a software provider, we are not only responsible for our organization security, but also all the customers that we deliver the software to. Also, companies must adhere to various industry-specific regulation and compliance standards, such as SOC 2, ISO, and NIST. And emphasizing a strong supply chain security posture not only mitigates the risk of regulatory non-compliance, but also demonstrates a commitment to data protection and security, enhancing organization reputation and trustworthiness among customers, partners, and regulations. So, attackers are often motivated to compromise a single library within the supply chain because the potential of a widespread impact. By infiltrating a popular dependency, they can target countless software applications and systems. Potentially, accessing valuable data or systems in various industries, this tactic exploits trust in commonly used libraries and making detection for security teams more challenging. So, of course, this is a simplification, but cyber adversaries have been known to exploit vulnerabilities within package registration systems by registering, seamlessly banning variations of popular packages. For instance, some packages manager permit the registration of packages including Unicode characters, thereby enabling attackers to create similar-looking package names. This deceptive tactic potentially leading them to install malicious code. An example scenario could involve attacker compromising or controlling a well-regarded blog post or popular Stack Overflow answer. The developers will copy this command, like pip install some library, into a terminal, which probably enables you to paste Unicode, and will install the malicious package, will result maybe in a persistent Trojan. And the dependency confusion attack is when an attacker successfully uploads a malicious package to a public or a private package repository with a name that matches an internal or private package used by the target organization. And also, Recently, some package managers were vulnerable to disclosing if a private repo exists via a timing attack. And repo jacking is an attack where a malicious actor registers a username and create repository used by an organization in the past, but which has since changed its name. Doing so results in any project or code that relies on dependencies and the attack project to fetch the dependencies and code from the attacker-controlled repository, which could contain malware. By the way, repo jacking was a mitigation that was bypassed like 4 times in the last 2 years. And where is my mouse? No, seriously, where is my mouse? Here it is. So, the tampering vector. The Ruby package manager, RubyGems, was vulnerable to a guessing attack, where an attacker could eventually override the next version of any package. In NPM, which is the node package manager, 2 years ago had a similar vulnerability that also allows an attacker to publish a new versions of any package. A couple of months ago, NPM registry suffered from a security lapse called manifest confusion, which allows a threat actor to modify the manifest data submitted with a new package to remove dependencies and scripts so that they do not appear in the NPM registry. However, the scripts and dependencies still exist in the package.json file that will be executed when the package is installed. And also, let's not forget that compromising a domain, navigating to a forgot password service, clicking the validation link could lead to a theft of the repository package manager credentials. And a lateral movement from the artifact storage server or CI to the entire SDLC ecosystem, compromising your build environment. There are many ways to inject malicious code during the build before turning into the artifact, like what happened in SolarWinds and 3CX. This is a vulnerability the Sonar source found on a popular CI/CD named TeamCity by JetBrains. So due to time constraints, I will not show all the case studies from the last 2 years. Those who want to hear more are welcome to reach me out after the talk. But Pipey suffered from a phishing campaign targeting popular package manager maintainers, directing them into a login screen from a mail that was not from the official Pipey domain. A couple of weeks later, there were posts to buy legitimate Pipey accounts in a popular dark web marketplace. And the artifact storage. Well, the artifact storage company we decided to search was one that we are using. They take their security very seriously. The SLA in their bug bounty program on the paper is 2 days, but in practice it's more like 2 minutes. The specific product has a couple of serious exploits in the wild, in older version, of course. We're going to talk about a couple of CVEs we found, but also a couple of duplicates. One of them was a way to bypass a brute force mitigation, and during the research, we tried to find the root cause of a recent medium severity CV, which we turned into a critical one because we successfully managed to elevate privileges. So let's start with a primitive we found that can be used in a phishing campaign. Basically, we found a way to enumerate users for the specific instance of the product, and we control the mail content. The mail will be sent from the artifact storage instance, which is a trusted domain, not like in the Piper one. By the way, finding targets, instances of this product in the wild was easy thanks to Shodan-like search engines. Also, finding the managed one is just enumerating the subdomains of the company main domain. For those who like numbers, we saw like 30,000 servers in the wild, with average of 10 users per server. A couple of them had like 500 users for that specific artifact storage product. Well, we can't yet deep dive into where the bug is, maybe in a future blog post, but anyway, it's less interesting, but the LP was more interesting. So, let's assume we caught someone in our phishing campaign. So we can now log in as a user, but we don't have any privilege to upload, which means we can't tamper the artifact that will be delivered to our customers, their customers. We can't tamper it yet. The first thing, us as attackers, so the first thing that there is a default user named admin. It's the first user. So our next step will be to generate a token for that user. Everybody can see it well, hopefully. So we will trigger the forgot password for that specific admin. By the way, if the admin changed its name for some reason, we have the primitive to enumerate users, so eventually we will reach it. So we will post a request to the forgot password service and provide a username. A token will be generated in the database. It will contain, so if we will have that token, basically if we will have the mail that the admin will receive, we can jump to this link and reset the admin password, and then we won, but we don't have it. So the token that will be generated in the database will contain a base64 of a UUID version 4 and a timestamp. This token will be valid for half an hour. That's why it contains a timestamp. If we had that token, again, we could reset the admin password. So now we need to find a bug that we can exploit to leak this token. Keep in mind that we download all the versions of that product and it contains symbols. It's not obfuscated, which is nice, and we can easily understand when something was changed, was deleted, or removed in each version. But we need to enumerate the attack surface, understand which request can be made from a non-privileged authenticated user, and we decompile the product. We found the main server, but I'm too lazy and it's too complicated product, many files, many services. As you can see in this picture, what you can see is me trying to grab services that have like the rules allowed annotation with the user, which means this is a request that the user can reach, can execute. And grabbing this is possible inside the IDE, but many false positives will arise because there are additional checks in the path, like checking if you're a repo manager or checking if you're an admin and so forth. So what we did is we teached an AI, an LLM. This is the Code Llama version 2. We used the LLM to sort the attack surface paths by complexity. Code with many constraints and ACID, which means attacker-controlled input data, gets higher score. I'm also a strong advocate for patch diffing, digging deep into the pinpoint, the underlying root cause of the known vulnerabilities, and harness this insight to detect new variants. So if the path contains an old bug inside the path, it will be taken into account when scoring. So after sorting the attack surface, it was time to audit it manually. Eventually, we found a good old SQL injection inside a proprietary query language parser, which means it was a complexity, very complex path. Well, when adding a filter, as you can see here, when adding a filter, we control the order by columns, which luckily for us had no constraints. So just a word about the database that will be used in that product. The database inside the product will execute this query. Does not allow to chain queries. So we need to complete this select query. And we can only control the way it's sorted. So when we query as you can see here, for all bundles for the user that we caught in our phishing campaign, we will view and we can control only what is sorted. This technique is known as blind Boolean-based SQL injection. We can use this primitive to leak the admin reset password token. What we will do is, iterating each letter of the reset password token, and we'll compare against each option. Basically, imagine that we can see what is returning, and we can view by the way it's sorted each letter. Like, we get the admin reset token, which is base 64, so basically alphanumeric, and we check the first letter if it's equals to A. If it's equals to A, it will be sorted the way we want. If not, it will be sorting the other way. So, and then when we get a hit for the admin reset token letter, basically we'll continue. And this technique, basically, as I said, the token is a base 64. We have 52 letters, 10 numbers, 3 special characters. So executing this number of requests on a remote server, on average, will take us more than half an hour. So we needed to optimize it. There are a couple of ways to optimize it. I will show you the way we used. So each character of the token is 1 byte. Well, the most significant bit will be always 0. So we can iterate each bit for each token and just ask, are you on? If you will be on, it will be sorted the way we want. If not, the opposite. And so using this technique, which you can see here in a pseudocode, was way better and let us leak the token that was valid for half an hour. So we could get a token and reset the admin password. So many times attacks are discovered by a good EDR or other means, only after the customer has been compromised, like the 3CX, or the 3CX attack was first detected by an EDR. This is an important note because the whole incentive of defending against those kind of attacks and preventing them to reach your production environment and your customers. There are also many examples of maintainers that want to monetize the time invested on developing the library that is being used by many organizations by performing a line of service or crypto mining, or what happened lately in a popular C# testing library named Mock, which the author just decided to exfiltrate data from developers and sell it. So who is watching if the author or one of the contributors' credentials are on sale, or just the author gone rogue, like in protestware? And in this example, this is a maintainer that deletes a legitimate issue that points out a suspicious commit. And also, not every repository has 1,000 eyes like the Linux kernel. And even there, students from Minnesota University intentionally introduced the use after free bugs into the kernel. We also saw many cases of developer using latest minor or even latest in general. Well, updating allows you to benefit from bug fixing, improvements, and new features, but also new attack surfaces and new bugs. Many discovered bars are variants of previously reported vulnerabilities that the patch wasn't hermetic. So everything I just covered relates not only for the first level of dependencies, but also for the transitive dependencies, those first level dependencies use, and so forth. So before we talk about malicious attack detection, you all know about vulnerabilities. This is something you probably already checked today with an existing scanners, but vulnerabilities are usually non-intentional. Let's talk about how to detect malicious by definition attacks. So malicious code detections can be a few ways to detect such scenarios, like in static code analysis using rules, or heuristic. Did somebody push without a review at midnight? Is it the first time they're modifying this area? Well, you can also teach a machine learning, teach it to learn malicious patterns and cluster it, for example. And the thing here that comparing artifact to the source code is super important. And it's a very complex problem, at least for compiled languages. In most cases, Python, for example, it's rather easy. We can compare text to text, right? But let's take Java or C#. How can we trace and know for sure that a package compiled code corresponds to the source code it came from? What if somebody tampered with it, utilizing one of the attacks we spoke about just before? To tackle this problem, you can either use reproducible builds, which have been proved to be very hard and not deterministic. And we can convince all the open source project maintainers in the world to verify each and every step in the artifact and the development build process, which is kind of not realistic. Or we can perform a binary to source compression. Using reverse engineering, many heuristics are needed to retrieve information loss due to a compiler optimization. Or you can teach an AI to do such thing, but that's a whole different presentation. Or you can just write and go, where you can bring all the source code to your computer, compile it, go to lunch, and then come back and we will probably finish. But as I showed you before, as we did, someone can compromise your CI/CD, as we shown. So that's it. Thank you for listening, and if you have any questions, please don't hesitate to reach out. I'm here.